One of the great things about CPLEX OPL is that it doesn't actually require us to write the same equation over and over and over again when our equations have some sort of structure. Right? And specifically what I mean by that is whenever we have equations that involve sums, or we have some equation that we repeat over and over again over some set of values, then we don't actually have to write each line of the LP. Okay, so let me sort of give an example problem, and we'll actually end up programming it in CPLEX. All right, so the way we're going to study this, or sort of learn about how to use sums and what we call foralls in CPLEX, is through the standard transportation problem. So, as you might recall, the transportation problem looks something like this. We have a series of, let's say, depots, storage depots, that have a supply of some widgets, and that supply is S1, S2, all the way to Sn. Okay, so, or Sm. These are given. So, one is 5, one is 10, one is 20. Those for each of the depots. We also have a bunch of destinations. And here we can have n destinations, so they don't have to be the same. Now, each destination, there is a corresponding demand D1, D2, all the way to Dn. Now, the goal is to get all the supplies to all the demand, to satisfy all the demand. And to do this, we can sort of transport those goods along the network. So here we sort of see the case where Depot 1 can ship goods to Destination 1, Destination 2, 3, 4, all the way to N. Now, the cost of transporting goods along this network is given by the weights on each of these connections. So we'll have something like C11, D12, C1N, and then similarly we have C21, C22, C2N, and this sort of repeats for all these source and destinations. All right. One of the big assumptions that we do have to make, just so we're clear, is that the sum of the supplies, okay, so let's say the sum of Si from 1 to M, that's going to be equal to the amount of demand. So we're going to have a balanced problem. Now, certainly, one of these supply nodes or the demand nodes could be sort of like these false fictional ones. That either absorb the extra or produce extra. Okay, so this is the requirement. So if we go back to our original formulation, we can actually write this as an optimization where we say we want to minimize the double sum of I from 1 to M and J 1 to N of the cost of each IJ transport times Xij. Now here Xij, this corresponds to the let's say amount transferred or transported from supply I or depot I, whatever you want to call it, to the destination, or let's say the demand. Actually, I should probably have written that the other way. Let's see. Destination J. Okay, so that's going to be our decision variable. All right. Okay, So we're going to minimize this double sum, and we're going to be subject to some constraints. And basically the constraints are going to go node by node. So at this supply here, the amount that goes out along the network has to be equal to the total supply available at that depot. Okay, and this is going to be true for every single one. So we're going to say, for S2, or the depot 2, the supply that goes out has to equal S2. And similarly, for M, the supply that goes out has to equal SM. All right. So we can sort of write this in a compact way by saying, for all of the i's from 1 to m, the sum of j equals 1 to n of xij is equal to si. Okay, so effectively what we're saying is, no matter which I you're talking about, which of the depots, the sum of the, let's say, amount of product that's getting transported out of that supply has to be equal to the amount of supply there. Okay, and so what we see here is, instead of writing the supply constraints for each node, we can just, over and over and over, m times, we could just do it one time. Similarly, we can do the same thing at the demand side. So we know at each of the destinations, the amount of product that gets fed into that destination has to equal D1. All right? So we can write that by saying the sum of all I to m of xij is equal to dj for all j equal to 1 to n. Okay. Now again, we could have done this individually. So, if we were to do this sort of expanded out, which would be crazy, we might have something like minimize. And I'm going to just do it with 2 depots and 2 destinations. So we might have 5, 1, 1, plus 3, 1, 2, plus 6, 2, 1, plus 10, x, 2, 2. So that would be my cost function. We'd then have some constraint that would say something like x, 1, 1, plus x, 1, 2 is equal to the amount of product at warehouse 1. So let's say we had, 5 products at warehouse 1. In warehouse 2, maybe we have 10. Okay. All right. So this is the same thing as we should actually write this. These are the supply constraints. And this is the demand constraints. Okay. So here go the supply constraints written out. And I just sort of made up numbers here. Okay. The demand constraints look a little bit similar, but they're going to index a little bit differently. So here you can see we're indexing on the J, right? Which is what we did here, right? So we're summing across the J. At the destination nodes, we're going to have something similar. So we're going to have x11 plus x21, let's say, is equal to 7, and x12 plus x22 is equal to 8. And of course, we require all xij to be greater than or equal to 0. Okay, so what does this problem look like? Well, again, this is sort of a 2 by 2. All right, and if we were to draw this network out, it would look something like this, where the cost of transporting goods from 1 to 1 is 5. from 1 to 2 is 3, from 2 to 1 is 6, and from 2 to 2 is 10. All right. The amount of supply at depot 1 would be 5, so S1 is equal to 5. Here S2 is equal to 10, and then the demand would be 7 and 8 respectively. Okay, so I could certainly write that all out, but why do that, right? We have this general formulation. Oh, and actually I should, this is the demand constraints. Right. We have this general formulation, and what if I had hundreds of supply depots and hundreds of destinations I could do? This would be a real pain to write out all the equations, right? So in total, we would, if we had M supplies depots and N destinations, we would have to write M plus N constraint equations. So that's really painful. So the good part is, again, CPLEX lets us sort of simplify this, all right? And so CPLEX has a way where we can write out sums in sort of a simplified way, and more so, we could sort of do these for all I in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or for all j. We could write these types of constraints really easily in CPLEX. All right, so let me give you, first I'll start by giving the standard form for how do we write sums in CPLEX. So it's kind of neat. The way we do that is in CPLEX you write sum, and then you'll write, you'll give the name of some sort of index counter. So you could do I, right? And you're going to say for this index counter inside of some range. And I think you can even use a set if you wanted to. All right. You could also do double sums. And the way that you would do that is you would add another index. So maybe there's index 1. We might add another index 2. In range 2, right? And you could keep doing this, right? So if you wanted to sum over like 5 different variables, you could certainly do that. And then what you're going to end up writing is your equation, whatever that equation is. And this could even be a constraint if you want, right? Again, if you don't remember the notation, whenever I write these sort of brackets, that means that's like fill in the blank, okay? So you replace the brackets and whatever's inside with what you want. Okay, so what does this look like in practice? So let's say I wanted to do a simple sum like the sum of I equals 1 to 10 of xi equals 5. So maybe I have this constraint. I could write that as, all right, so in CPLEX, what we'd write is sum I in 1 dot dot 10. We'll close it off. And then we're going to say xi is equal to 5. Okay, so these two are equivalent, and hopefully this makes some sense to you. We could certainly make things a little bit more complicated. Let's say we had a cost function where we're doing a weighted sum. Right, so, this is what we normally do in an LP. So, and in fact, we could do it over a set. All right, so I think we can do this over a set. So let's say we had the sum of I in my cats, right? And we could multiply ki times xi. And again, really my cat is probably a range. But we give it a fun little name. So let's say this was our cost equation. So we could just write that as sum I in my cats And again, this is just some range that we might have defined earlier. And so we'll multiply ki times xi. Okay, so it certainly works. And again, the assumption here is this is sort of a constant. And this is our decision variable, this x. So sorry, I should be pointing at the x. Okay. Certainly we can do double sum, so I sort of indicated that that's something we could do. So let's say we had the sum of I equals 1 to m and j equals 1 to n. The way we would, and we're going to say xij. So maybe this is less than 5. Okay, so I'm just sort of making things up. The way we would write this is just sum I in 1 dot dot m. And maybe m is a value we actually defined earlier. So m could be set equal to 5. Or m could be set equal to 20. Whatever we want. Right? And this is the nice part about the OPL language, is that we could solve our problem and then change the parameters, right? So maybe we want to sum over 10 depots or 5 depots. We could do that and rerun our code pretty quickly. So here we're going to say j is in 1 to n. I'm going to say x I comma j is less than or equal to 5. Okay. So if there's a constraint, all these will require some sort of semicolon afterwards probably. I'm just sort of dropping them because, it looks a little bit messy when we're writing on the screen, but keep in mind we always need semicolons. All right. So we've learned how to do sums. The one thing that we quite haven't learned how to do, that we still need to do, is how do we write a constraint like this, where instead of explicitly writing out the constraint, each equation one by one, we can sort of say, hey, this general constraint holds for all j from 1 to n. Okay, so that's what we're going to do. And so this is actually pretty easy. So let me scroll down here. And we do this using the Forall sort of command or statement. Okay. So I think the best way to learn this is just by an example. So let's say we wanted to sum xij, and we want to set that equal to si. And this equation is going to hold true for all I in 1, 2, 3, all the way to m. Okay, so there's some set that I is in. All right. So again, this one statement actually represents m different equations. Okay. So instead of writing it out m times, we can use this for all statement. And the way it sort of works is we say for all parentheses I in 1 dot dot m. Okay. And then we just write out our constraint like we would normally. So in this constraint, we're going to say that the sum of j in 1 dot dot n of x ij is equal to si. And so these end up being equivalent formulations, and we're going to have a semicolon right after that. And it's actually pretty easy to do. All right. Now, we can certainly do nested statements with the Forall. So it's certainly possible. Let's say we are, had some constraint where our x was actually three-dimensional. So it was xijk. So these things certainly happen. So maybe we have a constraint that says for all I in 1 to m, and for all j in 1 to n, the sum of k in, 1 to o, xijk is less than or equal to 6. Okay, so this would be the equivalent of saying the sum of k from 1 to o of xijk is less than or equal to 6 for all I in 1 to m and j in 1 to all the way to n. Okay, so these are sort of equivalent statements. And so hopefully you can kind of capture the structure of what's going on. All right, the next part of this video, what we're going to do is we're going to actually program in a transportation problem so you can see how this works in practice. Now, I already have CPLEX opened up, and I created this file called simpletransportation.mod, and you can see it in the run configuration. Now, the way I'm going to do this is by kind of doing it how you might actually do it. For this problem, I'm just going to start by defining a few variables. All right. Now, the way we go about defining the variables, again, we say the type, we give the name, and then we assign it a value. So I'll start by saying m is equal to 4. All right. And so for the supply problem, let's go back here. M corresponds to the number of supply depots that we have. Similarly, we can define n as the number of destination nodes. Here I'll use 3 just for simplicity. The next thing that we can do is we can start to define ranges. Right? Range. So maybe we can define a range of depots, and that's from 1 to m. This will become useful later on. And we can define another range of destinations from 1 to n. Why am I not allowed to do that? So, yeah, casing. Okay. So good to know. Apparently OPL is case sensitive, so now we know that. All right, so once we have the ranges that are going to correspond to the destination and the depots, maybe we can define the cost of transport. All right. So in this case, we'll make a float. We'll call it C. And this is going to be a multi-dimensional float. And so the dimensions of C are going to be depots by destinations. Okay. Okay. So we'll do depot by des. Okay. And again, it's going to be important that these are both ranges that can be referenced. All right. So for now, I'm just going to type in a matrix manually. So I'm just going to make up numbers. And again, it's going to be a 4x3 matrix. So I need a few different rows. All right, so we got our cost matrix. The next thing that we need to do is define the demand and supply at each of the depots and destinations. So I'll go ahead and make another float array. And so we'll call this one S, and this will correspond to all the depots. And maybe the supply at these depots is, we'll just make them all 10. So we have 4 depots. So 10, 10, 10, 10, 10. At the demand, we'll call it D. These are at the destinations. Let's make this a little bit funny. So we need to add up to 40. So we'll do 15, 5, and 20. All right. The last final step in the definitions is we're going to need to define our dvar, our decision variable, xij. Okay, so for x, again, it's going to be defined according to how many depots and destinations that we have. All right, great. Okay, so hopefully this stuff you already saw before and kind of remember. The next step is going to be writing out our cost function on our constraints, and we'll do this using the double sums and the Foralls. So first let's start with a minimize, and what we want to do is minimize the double sum of Cij times Xij. So we're going to minimize the sum of I in depots, comma j in destinations, of C I comma j times x I comma j. Right, that's pretty simple. We're going to now do that subject to some constraints. Now the first constraint again is the supply constraints. So here, if you remember, they have to hold true over all the I, and then next for the destination constraints, it holds true over all the j from 1 to n. The first constraint then is for I in depots. Right? Now you can actually, usually pretty good practice to just press return. And it's here you'll write the actual constraint. So in our case, the constraint is sum j in destinations x I comma j is equal to s I. At this point we can wrap it up with a semicolon. And something it did not, oh, equal. Okay. We can do the same thing for the demand constraint. So instead of depots, it's des, and we should change this to j, and we're going to sum over I in the depots, except now we're going to set it equal to the demand at each destination. Right. And that's all there is to it. We've now shown how you can use for all statements and some statements to write these programs. Now, the one thing that's missing is we need to find a better way to enter in these variables. But hopefully you're seeing sort of the structure, Because what's going to happen is we're going to load in this data from another data set, and it will automatically know how many depots and destinations there are, what the cost functions are. Okay, but we can go ahead and run this, and we'll go ahead and get a solution. There we go. So you can see X is actually written out as a matrix right there. Now, hopefully, I think I might still have this writing out an LP. Did it actually do that? No, it didn't. So if you want, you can have this sort of, again, create the LP file automatically when you run it. But for some reason, I don't have that set up. That would be interesting to look at. And what you'd see, actually, if you did that, is you would see every single constraint equation written. So I took a minute or two to remember how to create the LP file, because I actually do think it's worth seeing what gets generated. So if you guys don't remember, in order to create the LP file, the first thing you have to do is create a new settings file. Now, I already have a settings file here. You can see it because it's called .ops. And what you're going to want to do is drag that into your configuration. So I'm going to add that setting to the configuration. Now, the key setting that you have to change in the create LP OPS, so I just double clicked it, is you're going to want to go to run. And here you can see there's a export format LP. And so that should do it for you. So just set this to LP. Okay, so I'm going to close this. I'm not going to save it because I didn't really change anything. But again, I drag this into the configuration that I'm running. So let's go ahead and run that. Now you can see it actually created, oh, that's terrible. I just called it configuration 3.lp. So let's see what's inside of here. And sure enough, what you can see is a linear program where it writes out every single one of the constraints. So again, we see 4 supply constraints, 3 of the demand constraints. There goes the cost function. Right. So it sort of writes out how you would algebraically write it out. So that's how you do sums and foralls in CPLEX. Pretty straightforward. Again, it's sort of building on what we already know. And the next step will be sort of loading in data.